Okay, so we're continuing our work on approximation algorithms. Last time I showed you more about approximation schemes, these techniques for getting really, really close approximations to a variety of problems through rounding, enumeration, and dynamic programming. And then I started on the next topic, which is but today we're really going to be devoting the entire lecture to just learning how to relax. So this should be a relatively pleasant lecture for everybody. Lay back in your chairs, stretch out your legs, get nice and comfy. So we talked about relaxations, where you go through this process of loosening the constraints, so let me be redundant here, but you relax some of the constraints. Okay, but only some of them. You try and keep enough of the constraints in the problem so that the sort of fundamental nature of the problem hasn't changed. It's just gotten a little bit, you just got a little more flexibility in coming up with your solutions. Right? Then you find a solution to the relaxed problem. Right? Now notice that since we're relaxing constraints, we're making them looser. The objective only improves. Right? If it's a minimization problem, the value you can achieve gets smaller. For a maximization problem, the value you can achieve gets larger. Right? You find an optimum of the relaxation. And that means that it's going to be better than the original opt. But it's not feasible. And so what you do is you find some way to round that relaxed solution to a truly feasible solution. And when you round your solution, right, it makes the objective worse. Right? But however much it's making it worse, you're starting from a better than optimal objective. So if, for example, and that means that you can bound the quality of your rounded solution versus opt by comparing to the value of the relaxed solution. So if rounding causes you to at most double the value of your relaxed solution, well, you know that it was previously better than opt. So after doubling, it's at most twice opt. And so whatever ratio you achieve against the relaxed solution is also a ratio that you achieve against the true optimum. Right? And so we saw this last time with TSP, traveling salesman problem, where we used the minimum spanning tree relaxation, right? And we showed first a 2 approximation, and then a 3/2 approximation to the minimum spanning tree. That is, we found a solution that was at most 3/2. We found a solution which cost the minimum spanning tree plus at most half of the optimum TSP tour, and so that gave us something which was a 3/2 approximation to the optimum TSP tour. Okay. Now I said this quickly last time, but let me just revisit it quickly now. Recently, there's been further progress on this problem. People have been able to achieve 3/2 minus epsilon, slightly better than Christophanides' heuristic. Alex Madry was one of the people who was involved with that. They found better ways to relax the problem. They found a less relaxing version of the problem. Instead of relaxing to an arbitrary minimum spanning tree, they looked for something they call a thin tree. It has to be more path-like. It can't be a big bushy tree. And they show that because it has more path-like nature, it's easier to round it to an actual tour. You don't sacrifice quite as much in doing that. Okay? Now, for a long time, there's been this idea or this approach to the traveling salesman problem known as the held cart bound. The idea of the held cart bound is, again, to tighten the MST relaxation using something like prices that we saw in min-cost flow. The idea of the held cart bound is to say, well, you're allowed to put prices on the vertices as long as all the prices sum to 0. And now what you do is you declare the reduced cost of an edge. You add the price of the two endpoints of that edge to the cost of the edge, and that gives you a reduced cost for that edge. Now, if I do that, if I assign a price to every vertex and now create reduced costs for the edges, where the price is summed to 0, what does that do to the cost of the optimum TSP? Yes?
It should not change it because you just added some stuff that adds up to 0.
Exactly, right? On the optimum tour, every vertex is on two edges of the optimum tour. So when I add the cost of endpoints to every edge, I'm basically adding twice the cost of every vertex to the entire tour. So if this price is summed to 0, this has had no effect. So these reduced costs don't change the cost of the traveling salesman problem tour, of the optimum TSP at all. Okay? But what you do is, so one intuitive way to approach this is to say, let me look at the minimum spanning tree. Okay, why is it not a tour? It's not a tour because there are some high degree vertices. So what am I going to do? I'm going to increase the cost of the high degree vertices and decrease, and conversely, there are too many leaves, right? A path only has 2 leaves. The problem with a minimum spanning tree is that it may be a bushy thing with lots of leaves. So what I'll do is I'll make the leaves cheaper, and I'll make the high degree nodes more expensive. And this will encourage the minimum spanning tree to reduce its degree on the expensive nodes and increase its degree on the leaves and hopefully become more path-like. Okay? And you can actually design an optimization problem for finding the very best set of prices for doing this kinds of transformation. And it is conjectured that this actually gives you a 4/3 approximation to the minimum span, to the traveling salesman tour, right? Significantly improving on Christophanides' heuristic. And there's been a lot of work, and nobody's ever found a counterexample to that, but also nobody has been able to prove that it does this well. Okay? And I'll come back to the held carp relaxation after I've taught you a bit more, because there's another way to look at the held carp relaxation, which is also quite interesting. Right, and I also talked last time about the directed version, where for a long time the optimum was an order log n approximation using what's known as a cycle cover relaxation, which you will encounter in your homework. It recently was improved to log n over log n. And finally, I mentioned that the Euclidean traveling salesman problem, where you're talking about traveling among points in Euclidean space, that has a polynomial approximation scheme using the enumeration techniques that we covered in this class. And After Thanksgiving, I won't be doing required lecturing anymore. I'll let you focus on your projects, but I might give some optional lectures, and maybe I'll show you a little bit about this polynomial approximation scheme. Okay, so now what I want to do is show you one more of these really nice relaxations. And for this, we're going to go back to scheduling theory. So as a warm-up, I want to look at the problem known as one some Cj. So for those of you who remember the scheduling notation that I introduced you to, what scheduling problem is this describing? Yes?
It is a single machine scheduling problem that aims to minimize the sum of n times.
That's right. So one machine, and your objective function is the sum of completion times. Now, why would you be interested in the sum of completion times? Well, suppose that I put a 1 over n outside of the sum of completion times. Then what am I measuring? Yeah? Average completion time, right? So this is just trying to get the jobs done as quickly as possible on average. Okay, if your jobs represent customers, right, you maybe can't satisfy everybody, but you may want to satisfy as much, you may want people to be as happy as possible overall. Okay, so average completion time is a reasonable objective. Any thoughts on how we might try to do this? What would be a good strategy or a good heuristic for optimizing your average completion time? Yes?
We just do like the shortest jobs first.
Right. So it turns out that a very good strategy here is what's known as shortest processing time. SPT. Any intuition on why this is a good idea? Yeah?
If you're doing the shorter tasks, then the other ones aren't waiting for a super long time for them.
Exactly. The point is that whatever your order of jobs is, right, any job that's later in the order has to wait for all the jobs before it, and all the jobs before it contribute to its completion time. So by putting the short jobs first, you minimize the amount that all of the other jobs later in the order have to wait. Okay? But we're going to have to formalize how well this does. Okay? And it turns out that this is actually optimal. This gives you the exact optimum solution. Okay? And the proof is actually not very hard. Let's consider the optimum. And let's suppose that it is not in shortest processing time order. Okay? So that means that somewhere in the order, some job Pj is longer than the Pj plus 1, where here I'm assuming that I have re-indexed the jobs by completion time. Okay? So we've got a bunch of jobs that run. Then we have some job that takes time Pj. And then immediately after it, we have a shorter job that takes time Pj plus 1. And then we have more jobs. Okay? So how do I get a contradiction to my assumption? Yes? Exactly. If we swap these two jobs, right? Okay. This changes no other Cj. Right? Nothing else has changed in the schedule. It's a purely local change. Right? Now, under this swap, Cj, I guess I'll say Cj prime, is equal to the old Cj plus 1. but C prime j plus 1 is strictly less than Cj. So we've decreased one of the completion times without increasing anything, and so we've got a better schedule. Okay. Now, so it's a straightforward proof by contradiction. Note that I haven't proven that a locally optimal schedule is globally optimal. That's often not true. But I have shown that in this case, if you are globally optimal, then you will also be locally optimal under these swaps. Okay. All right, so this is really cool. We have an algorithm that gives you an exact optimum solution to one sum Cj. So what does that tell us in the context of what we've been studying? One sub Cj is not what? It's not NP hard, right? If we can solve it with an exact polynomial time algorithm, then it's not an NP hard problem. So what am I doing introducing you to a not NP hard problem in the middle of the approximation algorithms lectures? Well, one answer is, as we'll see on your problem sets, sometimes you use approximation algorithms for polynomial time solvable problems if the polynomial is too large. Now that's not the problem here, right? This is trivial. You just sort the jobs, okay? But now that we have that, I can talk about a generalization of it called 1rj sum Cj. Okay? And Rj means that you have release dates. Okay? For each job, there is a time before which you are not allowed to run it. Okay? And this problem is NP hard. So we're not going to find a polynomial time approximation. We're not going to find an exact solution for it in polynomial time. Okay. So why do these release dates sort of mess up the nice simplicity of the problem so that it suddenly becomes NP hard? What do the release dates cause to go wrong? I mean, I can try. Yeah, go ahead.
Sort of a relatively short job could be released very far into the future.
Exactly. SPT may say, run the shortest job at the beginning. But if that job has a later release date, you can't do that. Right? So what do you do instead? Right? There are a few different options, right? One would be to just wait until that job is available so that you can run it first. Would that be a good idea? Yeah? Yeah, there could be a ton of stuff that you could be running before, right? But on the other hand, it might be important sometimes, right? Like suppose all that's available at the beginning is a gigantic job. Should you run it? Well, it kind of depends, right? If while that gigantic job is running, all sorts of other little jobs became available, you might regret having started that job, right? Because it prevents you from running all of these little jobs. So all of a sudden, the problem becomes much more difficult. And you have to make this decision that, okay, there's a shortest job available now, but maybe I shouldn't run it. Maybe I should do nothing, just so that the machine stays free for jobs that are going to be available in the future. Okay? So how do we think about this problem? Well, for this problem, it turns out to be useful to think about a relaxation. Okay. What might be a relaxation of this problem of scheduling jobs with release dates? Well, what if we allow you to preempt? So preemption means that you can stop jobs midway. Okay? And later you can resume where you left them off. Okay? So how would we approach this problem? Yes? Right. So the intuition that we can get from one sum Cj is that you should run the shortest available job. Now, what does shortest mean precisely? Does it mean the amount, the length of the job, the original length of the job? Yeah?
It's until finish, right?
Exactly. So what's critical here is the remaining processing time. Okay. So it turns out that for this problem, shortest remaining processing time is optimal. Okay. And the proof is the same as it was for one sum Cj, except now we think about pieces of jobs. Sorry, I should be more precise about the algorithm. Basically, you're always running the shortest remaining processing time job, and if a new job is released and it has less processing time, then you preempt the job you're currently running, you put it back in the pile, and you run the shorter one. And now an even shorter job might get released, and you might preempt the one that did the preempting. And so you could have actually an unlimited number of preemptions happening, until eventually you take care of the short jobs, and then you go back to taking care of what's left of the longer jobs. Yes? Well, that's an interesting question, but notice that so you're running the shortest remaining processing time, and by running it, you're making it shorter. So if it is the shortest, it is going to stay the shortest until there's a new release. Right? So at the moment of a job being released, there might be a new shortest job, but you're never going to have to sort of jump back and forth between two jobs that have already been released. Okay? Good question. Okay. So how do we prove that this is optimal? Well, we're basically using the same argument as for one sum Cj, except now we think about swapping pieces of jobs. Okay. So again, we consider the optimum schedule. Okay. And let's suppose that you are currently processing some non-shortest job. So we're currently processing K while J is released and shorter. Okay. And so just as with one sum Cj, we're going to leave all the other jobs alone, and we're just going to think about the processing of job K and job J. We're not going to change the timing of anything else, right? So we're processing job K for a while, and then at some point we stop and process job J, and maybe we stop and go back to K for a while. Maybe we interrupted with something other than J and K, so we don't even think about it. We might do a bunch of Ks. Then we do J for a while longer, right? So on and so forth. Okay. And again, we're assuming, right, because we're assuming that we're not processing the shortest time, we know that job K has a longer remaining processing time at this moment than job J does. Okay. So I want to arrive at a contradiction by rearranging just jobs J and K as I did for one sum Cj. So what should I do in order to, right, I'm claiming this is the optimum schedule. What should I do to show that it's not the optimum schedule? Yeah.
Like that's enough. The sum of those interval lengths is enough to run both J and K. So you can just throw the shorter one to the to a prefix of these intervals that they're running on, and then that can only help your total response.
Exactly. Right. So we might as well ignore all the work that came before and just think of these jobs as both being released right here. Right. So in total, right, up to here, we're spending PJ plus PK work on these two jobs, right? Note also that however we rearrange this work, one of the jobs is going to finish here, right? And so this is the larger C whatever, right? Let me put an underscore here. So one of the two jobs is going to complete here. Okay, and that's true in the current schedule, and it's going to stay true. But what we can control is when does the other job complete, right? And if we process all of PJ first, right? So I send the K work forward and send the J work backward. Right? So if I do all of the J work first, finishes job J as quickly as possible. Right? Without changing the ladder completion time. So that's the way to, right? Under the constraint of only moving these two jobs around, right? Doing J first is clearly optimum for just minimizing the sum of those two completion times. And so if I'm not already doing that, then I'm not optimal. So does everybody now agree that shortest remaining processing time is optimal with preemption? Okay, great. Now, again, this shows that one RJ preemption sum CJ is not NP hard, right? We've just given a polynomial time algorithm for it. I won't fill in all of the details, but if you think about it, you can just imagine that sort of basically simulating the process, right? You know how long it's going to take for various jobs to complete. You order the jobs by their release dates. You sort of figure out when this job is released, am I going to be done with everything else, or is something still going to be running? And you basically treat it like a little event simulator, and you can execute the whole process just using a heap. Okay. But the question is, and so we also know that, of course, this is a relaxation of one RJ sum CJ, right? Because any feasible solution to the non-preemptive problem is a feasible solution to the preemptive problem. So all we've done is loosen some of the constraints. We haven't added any. And that means that the optimum of the preemptive problem is better than the optimum of the non-preemptive version of the problem. Okay. So we can find a preemptive solution, and it will be better than opt. What's the last thing we have to do? Well, we have to round. So how can we take this preemptive solution and use it to define a non-preemptive schedule? This is where the cleverest bit of this solution came up, right? Like, so in scheduling theory, it's really natural to use the preemptive version as a relaxation of the non-preemptive version, right? And it's very common for the preemptive version to become tractable because you're allowed to work in small pieces. It's kind of the simplicity of working with real numbers instead of having to make sure that everything stops on an integer, okay? But you have to figure out how to round, and that's where this gets tricky. Any thoughts? I've got this nice preemptive schedule. How do I make it not preemptive? Okay, yeah, a thought?
Order the jobs by the time they were first executed in the preemptive schedule.
Uh-huh, good. So that's very much in the right direction, right? If you think about it, the preemptive schedule is deciding on an order of the jobs, right? And so we can kind of use that to steer us. Now, it turns out if you think about it, ordering by their start times runs into some problems because essentially the start time is almost irrelevant because of all the preemptions that could happen after it starts. But it turns out that you just run the jobs in their order of their preemptive completion time. And this gives you a good schedule. Okay, so make the preemptive schedule, look at the order of job completions, run the jobs in that order. Now, that may mean that you insert idle time where necessary. So if your preemptive order says to run job 5 and job 5 is not yet available, you just wait until it is. Okay? So now we have to prove that this works, and the proof is really quite elegant. Okay? Which is also the analysis that tells us how well it does. Actually, let me phrase it a different way. Let me state a lemma that this gives us a 2 approximation, another 2 approximation. Okay. Proof is as follows. I'm going to take the preemptive schedule and show you how to make it non-preemptive. Okay. So take the preemptive schedule. Okay. And at time Cj, at the moment where job J completes, okay, I'm going to insert Pj additional units of time. Okay. So I've got this preemptive schedule that shows various jobs running at various times, right? And I can just think of it as a long piece of paper with the different job labels of which jobs are running at which times. There's going to be a moment where job J completes. I'm going to cut the paper right there. I'm going to slide down the later part and insert Pj units of time into the schedule. I'm going to do this for every single job. Okay. And on the one hand, I'm going to argue that inserting these Pj units of time, well, it makes it possible for me to run the non-preemptive schedule that I wanted, right? This inserted time is sufficient to run the non-preemptive schedule because that Pj time that I just stuck in to the time interval is enough time to run job J, right? Now, the important question is, how did this affect all the other CK, all the other completion times? Okay. Yes? Right. So we just have to add some clarity to that argument. That's exactly the right argument, right? So when we're thinking about other CKs, well, there's a couple of different things to think about, right? So jobs that finished before job J are completely unaffected by my adding work at time Cj, right? So really all that affects Ck are the jobs that finish before Ck, right? Jobs J such that Cj is less than Ck, right? Because if I insert time after, I'm not changing Ck at all. What is the total length of these jobs? Or the total processing time? Yes?
Well, they all finished in CK.
Exactly. All of these jobs finished before time Ck, right? They all finished. So the sum of those PJs is less than Ck, right? But this sum, right, the sum of those PJs, that's exactly how much time I inserted into the schedule before job K. So the amount of extra time that I insert before job J is upper bounded by Cj. And that means that every completion time at most doubles, thanks to my insertion of extra time. And that's the end of the story, right? This beautiful and simple rounding technique gives us a 2 approximation for 1 Rj sum Cj. Is that clear? Any questions? It turns out that this technique can be applied to much more general scheduling problems. Parallel machine scheduling and other side conditions can also be brought in. And still using this idea of looking at the preemptive version and then doing jobs in their preemptive completion order is beneficial. There are generalizations. So we ordered the jobs by when they completed. It turns out that there's a technique called alpha point rounding where you schedule based on how soon the jobs finished, say, 2/3 of their work, instead of waiting instead of scheduling according to when they finished all of their work. And depending on what objective you're trying to optimize, you can get better results. Now, for this particular problem, there actually is a polynomial approximation scheme for 1 Rj sum Cj. Okay. And this is, in fact, a couple lectures ago, I told you I met up with a friend at a conference and said, let's solve a scheduling problem. And so this is the one that we did. We took a walk, and we came up with an algorithm for 1 Rj sum Cj. And this problem had been open for 25 years, right, since it was defined. There was no such high-quality approximation. But in the mysterious way that research works, when we submitted our solution, 3 other unconnected groups from around the world also submitted solutions for 1 Rj sum Cj. And so there is now an 11-author paper, which we never actually met most of the other authors, but since everybody had the same result at the same time, they just said, smush all of your papers together. And so that's a fun little end of the story for that. And it's a polynomial approximation scheme. It uses the techniques that I showed you last time, the sort of enumeration, the rounding and enumeration, which is unsurprising because, as I told you, that's kind of the only way to get a polynomial approximation scheme. And so there was nothing sophisticated about the solution. It's just that with so many scheduling problems, nobody had gotten around to looking at this particular one and proposing how you would solve it. Okay. All right, so those are some nice relaxations, but they're sort of problem-specific relaxations. Okay, like, let's look at TSP. Okay, minimum spanning tree is a relaxation. Let's look at the scheduling problem. Okay, preemption is a relaxation. What I'm going to show you next is is sort of a general technique for relaxing a very broad range of problems. But let's get our energy back by taking a short break first. Yes?
I want to ask you a question about projects.
Mm-hmm.
Will we still have like P sets while we have projects?
No.
Okay. That's good. Otherwise, I would die. Nice.
Exactly. No. It's all the reason I'm lecturing 3 times a week is to get it all done before Thanksgiving, so you can focus on the project at the end.
I seem to have to write a lot of papers this semester. I also have to write one in machine learning class.
Uh-huh.
So.
You'll be busy. Yeah, we would be much better off actually if the classes were staggered, so different classes ended at different times instead of all ending at the same time. Another good one is diamond push-ups, where you put your hands together like this. That really gets the triceps. Well, obviously your thumbs aren't open enough. Diamond push-ups, it puts all the effort into your triceps, and you don't get any. It takes it away from your chest. So many people sitting down. It's just sad. Okay, let's resume. So, as I said, I'm going to show you a very general technique for relaxing NP hard problems. And for starters, let me go back to an example that we've already seen, a vertex cover. So everybody remembers the vertex cover problem, right? You've got a graph. You want to cover all of the edges with vertices, right? That is, you want to pick a set of vertices so that every edge has at least one endpoint chosen, and you want to minimize, right? This is implicitly a min problem. Minimize the vertex cover, okay? And we talked about a sort of an interesting super greedy algorithm for that problem last time. We are going to use a technique called LP relaxations. Why are they called LP relaxations? Because what I'm going to do is I'm going to write our problem as a linear program. Okay? So for vertex cover in particular, I'm going to have a variable xi, which denotes the fact that vertex I is chosen. Okay, so you can think of this as a Boolean, right? And now I can say, well, I want to minimize the number of vertices that I choose. That's just minimizing the sum of xi's, subject to a constraint that xi plus xj should be at least 1 for any edge, or for each edge, ij. Okay. Now, as it stands, this doesn't quite capture the vertex cover problem. Why not? Yes? They don't have to be integers. So to fix that, I'm just going to add a requirement that every xi be 0 or 1. Okay? And so I have now created what is known as an integer linear program. It's just a linear program with this minor added requirement that the solutions be made up of integers. Okay? Problem solved. We know how to solve linear programs. We're in great shape, right? No? Why not? Yes? Right, okay, so the linear programming solutions that we have will find these fractional solutions, but I mean, can't I just come up with some algorithm that finds integer solutions to linear programs? Okay, so what did I show you here? I showed you that I could solve the vertex cover problem by solving an integer linear program. So what has that proven? Yeah? So what in particular have I proven about integer linear programming? It's NP-hard, right? I've just given you a reduction, right? So integer linear programming is NP-hard. So if integer linear programming is NP-hard, what's the point? Like, why should I bother formulating NP-hard problems as integer linear programs? Yeah?
What if you round all xi which greater than 0.5 to 1 and all other xi?
Okay, so you're running ahead, right? So you're saying, well, if they're not integers, maybe I can do something about it. Okay, but right. So that's exactly the point, right? The integer linear programming formulation is NP-hard, but there's a rather obvious relaxation of an integer linear program, right? How do you relax an integer linear program? Yeah? Just don't require integers, right? Don't require integers. Okay? And that's why this is a good approach, is that once, if you take the integer linear programming formulation, you don't have to think about what the relaxation is. It's staring you right in the face, right? Just remove the integrality constraints, right? So we replace this with just a requirement that xi be between 0 and 1. Okay? And this is now the LP relaxation of the vertex cover problem. So when you have an NP-hard problem, formulate it as an integer linear program, relax it, and now all we have to do is rounding. Right? And here we're literally rounding. right? We have a solution that involves non-integers, and we want to turn it into a solution that involves integers. So how can we do that? Here's this fractional solution to the vertex cover problem, right? It covers the edges, but maybe only partly from each side. Where do we find ourselves in actual vertex cover? Actually, I don't even need another board for this. Let's just talk about the rounding. Yeah? Great. So because xi plus xj is at least 1, that means that one of them is at least a half, right? Okay. So set it equal to 1, right? If xi is less than a half, then we'll set it to be 0. Right? And this ensures that for every edge, at least one vertex, well, at least one endpoint is set to 1, right? Which means we get ourselves an integer solution that is a vertex cover. Now, how good of a vertex cover is it? How can we compare it to something and say it is not using too many vertices? Yeah?
It's the approximation.
Why?
Because the sum of x is our optimum, and this the optimum number of nodes we take in our cover. And if we increase every x, which is at least one half,
Mm-hmm.
then there would be no more than 2 times.
Exactly. Right? So again, the key argument is we're going to compare to the fractional optimum, right? Because we know that the fractional optimum is no worse than the integer optimum, right? So we no longer have to worry about the integer optimum at all. We're just thinking about the fractional optimum. Now, if we look at our rounding procedure, what do we do? If xi is less than a half, we set it to 0. That certainly doesn't make things worse. We only set it to 1 if it was originally at least a half, which means that every xi is at most doubling. Right? And if every xi at most doubles, then the sum of the xi's at most doubles, which means that our integer solution is going to be at most twice the fractional optimum, which means that we have a 2 approximation. Yes?
Is there any way to show that it can't be better than the children?
There is, but then you have to talk to those annoying complexity theorists. Okay? So yeah, hold that thought. Let me just make sure that we're done and everybody's happy with the algorithm. Okay? So we have a 2 approximation here. Now I'll note, this is actually better than we had before because this particular algorithm also handles the weighted version of the problem. Okay? Where there are costs for different vertices, and you want to minimize the cost of your vertex cover. Right? If you have costs or weights wi on the vertices, how do you generalize this approach? Yeah? Exactly, right? Your objective becomes minimizing the sum of wi times xi. You can still solve the LP relaxation, and you can still round exactly the same way. We still only double the xi's, which means that we double the weighted cost. Okay? So this is more powerful. Okay? Now, got asked, is there ways to show you can't do better? So first I will mention that this relaxation and rounding is tight in a really strong way. So you may remember that I told you last time that vertex cover is complementary to independent set, right? The complement of the vertex cover, the other vertices, form an independent set in that no edge has both of its neighbors in the complement because every edge has one of its neighbors in the vertex cover, right? So minimizing the vertex cover is maximizing the independent set in the graph, okay? And this LP that we've just defined, right, we wrote it as xi plus xj is greater than or equal to 1, which is the vertex cover formulation. If instead you say less than or equal to 1, you get the independent set formulation, which says at most one vertex can be taken in the cover. And I mention that because independent sets are also known as stable sets. And that linear program is known as the stable, or defines what is known as the stable set polytope. Okay, right? Every linear program defines a polytope, and this one is very intensively studied because it's a quite beautiful, simple polytope with a tremendous amount of richness to it. And a pair of researchers named Nemhauser and Trotter published some seminal papers on it, and they proved things about the vertices of the stable set polytope. Remember, this is an LP. It can have fractional solutions. And in fact, what they show is that all of the coordinates of every vertex of the stable set polytope are either 0, a half, or 1. Okay. Every vertex of the stable set polytope is some combination of 0, half, or 1. Now, it's a little confusing to talk about this vertices here because these are not the graph vertices. Right? So if we map back to the graph problem, what this says is that when you optimize even the weighted version, every single vertex is going to have a value of 0, or 1, or a half. Okay? And they proved even more. They proved that if xi is equal to 1 in that polytope, then I is in the optimum vertex cover. And if xi is equal to 0, then I is not in the optimum vertex cover. So in fact, the integer valued vertices have the correct values. But what you're left with, and I'm finally coming back to your question, is a solution for the rest of, right? You can take that part out, right? You can throw away the vertices that are not in the cover, right? And all of their neighbors will be in the cover because of the constraints. And you'll know that those belong in the optimum cover, so you'll take those, and you'll be left with some other edges that haven't been covered yet. And when you try to solve the relaxation, you'll get a solution where every vertex is given a value of exactly a half. And at that point, rounding will pay exactly a factor of 2 because you will take everything, and the actual solution is half the vertices. And that's where the NP completeness comes in. We don't know in a graph like that, there may be a vertex cover of exactly half the vertices, or you may need almost all the vertices in the vertex cover. And this LP relaxation cannot tell the difference. Okay? And so what that shows you is that there exist graphs where the fractional solution is 1/2 of the integer solution. And this question of the relationship between the fractional and integer solution is asked so often that we talk about what's called the integrality gap. The ratio between the integer and fractional solutions, and Nemhauser and Trotter proved that the integrality gap is 2, which says that you cannot possibly do better than a 2 approximation by rounding this linear program, because there are cases where the fraction will be a factor of 2 away from the optimum. Okay. Now, this does not close out the possibility that maybe there's a different algorithm for approximating vertex cover, but this is where the complexity theorists have really done some nice work. There's been a long line of work starting with Hastad in the early days. It was only in the 2000s that people began to figure out how to prove hardness of approximation. And again, a lot of the seminal work was done right here at MIT by Shafi Goldwasser and Sylvia Macaulay, a postdoc named Luli Safra. Anyway, he proved that you can't beat 7.6 unless p equals np. And then there was a sort of a series of follow-on results. Somebody named Cote et al. Proved that you can't beat square root of 2, okay, which is closer. And then somebody came along and proved something. They gave a conditional proof. They showed that 2 minus epsilon is hard if something called the unique games conjecture is true. And so that has led to 15 years of work by people trying to prove that the unique games conjecture is true, but we still don't know. But this has been the focus of a lot of attention in algorithms and complexity theory. On the other hand, there is a quite sophisticated algorithm that achieves 2 minus order 1 over the square root of log n. A little bit better than 2. And you might think, what's the point? Like, this is basically 2. But it turns out that this tiny difference is enough to drive all of our best algorithms for graph coloring. So graph coloring is another really interesting NP-hard problem, which I may introduce you to on the problem sets. Sorry, we talked about it in the additive approximations, right? That we showed that planar graphs are always or we talked about how they're always four-colorable. So it turns out that the best approximation algorithms for graph coloring use approximate vertex cover as a subroutine and only work because you can do slightly better than 2. So there's this whole edifice of approximation algorithms that's been building up, which rely on each other and on their hardness and so forth. So, any questions? Yes?
Vertices, all coordinates are 0, 1/2, or 1. Like, why can't one be like 1/3 and the other be 2/3?
They prove that that does not happen. Yes, in this formulation, that is, if you write down this formulation and you find any vertex of the resulting polytope, all of its coordinates will be 0, 1/2, or 1.
If you just like a simple thing where you have 2 nodes and an edge between it, and you have like one node have like 0.3 and the other.
But that won't be a vertex of the polytope, right? Remember, a vertex is where you have n-tight constraints. Right, sure, there are plenty of interior points in the polytope which could be arbitrary, but we showed the important role that vertices play in polytopes in linear programs, and so that's what they studied. Okay. Yes?
In general, if you relax like an integer linear program to a linear program, that the solutions that still have integer values will be the same in the optimal solution?
Yes, actually, that's a great point. So if you do a relaxation and you are then able to show how to that there is an integer solution, right? If you write down a linear program and show that there is an integer solution, well, that is also the integer optimum, right? Because the fractional, right, the linear program that removes the integrality constraints, right, is a relaxation. So if you're able to get an integer solution that's as good as that optimizes the relaxation, that is also an optimum solution to the original integer linear program. And so it is a true optimum of the original problem. And again, within optimization, people spend time showing that certain polytopes have integer solutions. Okay, and therefore there is no integrality gap. And the optimum of the polytope is the integer solution. We actually saw one of those polytopes. Does anybody remember a place where we sort of wrote down a fractional linear program, but I argued that the solution was always integral? Yeah? Max flow, right? So when we proved that there always is a maximum flow that is integer, what we were actually proving was that there are integer vertices of the max flow polytope, which is another polytope that has been studied a lot. Okay? And there are deep reasons that MaxFlow has that the MaxFlow polytope does have integer vertices. It's something known as total dual integrality. And there's unimodularity shows up there also. So people have studied large classes of linear programs where there is no integrality gap. And those are very useful because now you can get the integer answer by just solving a linear program. Okay. However, if the problem you're working on is NP-hard, that immediately tells you that there will be an integrality gap because otherwise P would be equal to NP. Okay? Other questions? All right, so I introduced you to this idea with a relatively simple and straightforward optimization problem, vertex cover. We are going to dive into this idea with a more challenging optimization problem known as facility location. So the last time I taught this course, the thing that everybody wanted at all times was boba. And I'm not sure if this is still true, but I will sort of work with that formulation, right? So this is known as the facility location problem. Okay. You have a set of customers who all want to be near a facility, and you have a bunch of candidate locations for facilities. Okay? And the idea is that you can open facility I at some cost, Fi. And now, once you've opened the facilities, you assign each customer to any open facility, customer J, to any open facility I at cost Cij. This represents, you know, the commute time or the amount of money that they have to pay to get there, or some other notion of the utility of that facility for that customer. Okay? And your goal is to choose a set of facilities and assignments, minimizing your total costs. Okay? I'll point out right away that we're sort of combining two possibly incomparable costs, right? It maybe cost you dollars to open the facilities, and you're talking about minutes of commute time for a customer. So you're going to need to think of some sort of translation that aligns the two costs. But you can figure out for yourself how do you want to rate these? How do you want to compare these two different costs into a single objective function. Okay? So this problem is NP-hard. You can actually set cover as a special case of this problem. You can think of your sets as facilities that you're opening to cover the members of the sets. Okay? So I'll write that in right away. NP-hard. Set cover as a special case. Okay. And indeed, this general version of the problem is so hard that we don't have a lot to say about it. Okay? Just like in traveling salesman problem, right? Traveling salesman problem had Hamiltonian path, a version of TSP with no costs, just structural. That was already hard. Similarly here, the facility location problem has set cover inside it, a sort of structural problem without costs, and we're just making it harder by adding costs. But a special case is the metric version. And that is easier. And so we are going to work on an approximation algorithm for the metric version of the facility location problem. This just says that theCij's form a metric. So the triangle inequality holds. And so if, for example, your facilities and customers are somewhere on a map in a place that is not Boston, then you can assume that triangle inequality holds, right? And sort of getting, right, if two customers are close to the same facility, then they're also close to each other, and so forth, right? And we're also looking at this this is a symmetric, of course, as well, your typical metric. Okay. So that's the problem we're going to try to solve. We're not going to finish today, but we'll get partway there. And so the first thing to do is to think about creating an LP relaxation for the facility location problem. So what should we do? Yes, question? That is a feasible solution, right? So that's worth talking about, right? I can open any one facility and assign everybody to it, right? This is going to be very cheap in terms of opening cost, but might be a tremendous connection cost or a tremendous assignment cost, right? It might be cheaper for me to open another facility near a bunch of people who are in a different town so that they don't have to commute as far. In the general case, but once we introduce this metric restriction, it becomes easy.
Even without the metric, we can't find any feasible solution, so it's not like...
Oh yes, so there is, even in the non-metric case, in the general case, there is always an easy feasible solution, which is to open all the facilities, right? That's feasible, unless somebody has an infinite connection cost, in which case there's no point, right? So yeah, feasible is easy, but optimizing is what's hard. Yes?
What is the cost forming a metric? How specifically does the triangle inequality?
Well, you should basically think of the costs as distances to facilities. Okay? Yeah, and so they imply distances between customers as well, right, via facilities. So how do we formulate an LP? Well, I mean, again, how do we formulate an integer linear? What is an integer linear programming formulation for this problem so that we can proceed to relax it? Okay, and we go through sort of a standard process here, right? We're talking about decisions about opening facilities and assigning customers, right? Decisions like that correspond to Boolean variables. And so we are going to define some Boolean variables representing those decisions, right? So I'm going to set yi to be equal to 1 if you open facility I. And again, this is for thinking, right? We're going to eventually get a relaxation, and we can't assume that we get 1s and 0s, but just for thinking. But 1 if it's open, and 0 if you close it. And similarly, we can define an xij equal 1 if you assign customer j to facility I and 0 otherwise. Yes? So these are our natural decision variables or indicator variables. Now we just have to ask, how do we write down the integer linear program? So what is the objective function? Yeah? Good. And of course, we want to minimize this, right? Yes? This is the opening cost. This is the connection cost. What are our constraints? Yeah?
Computers are between 0 and 1.
Good. So just looking ahead to the relaxation, right? The integer linear program would specify that they are 0 or 1. We're going to relax it to being between 0 and 1. What other constraints do we need? Yeah?
Each customer has to have a connection to at least one factory or facility.
Facility. Good. What does that, how do we translate that into variables?
Sum of xij over whatever the index is that I.
Right. Every customer has to be assigned to some facility, right? So this is saying that one of the, again, in the integer linear programming formulation, this is saying that one of the xij's has to be 1. Right? Yeah?
Xij is less or equal to yj.
Exactly. Or yi, right? So, sorry, let me make a little more space. So this is saying you assign to some facility. And saying that xij is less than or equal to yi. What is that saying? If we think in terms of integers. Yeah? Right, that you can only assign to open facilities. Right? And then, of course, we have the xij and yi's between 0 and 1. So there is our LP relaxation for the facility location problem. And we can give it to any LP solver and get a fractional solution. So all that remains is to round it. And that will take most of next lecture. Any questions? OK, half of next lecture. Yes?
Should we sum those two terms separately?
Yes. Sorry, I was sloppy here, right? This should actually be, this is a sum over I, and this is a sum over ij. OK. Anything else? OK, great. So yeah, we'll work on this next time. Just a slight advance warning, there's a vacation on Friday. So Wednesday will be it. And that's when we'll finish up with approximation algorithms. And we'll be able to start on our next topic the following week. See you Wednesday.